Welcome to the Middleware 2024, as I said, a place to talk, a place to present, and a place to contribute by everyone. Some small words before starting this. For the ones that don't know, the workshop on serverless computing has been for years here, like as the name may suggest, 10 years, okay? And so, and we'll have to correct something now because yeah, okay. Now, yes, sorry. The slides were
start as many times as you want.
It has been for years, 10 years now. It began at the ICD-CS 10 years ago, and it has been changing conferences for years until now. That has been pretty much established in the middleware conference. So for the ones that do serverless or kind of serverless technologies, just remember that it may be a place to present your things, like in a familiar ambient and everything. I am Germán, as you can see. I am co-chairing this session with Praveen, who's there. We have our co-chairs, Pedro, Paul, Batche, Vinod, and Alek. Thank you for your help and your commitment on this, because it was great, all the effort you put on this the last days. And also some accomplishments for the rest of the team, the steering committee, and Enrique, who is always updating and keeping the web page up to date. Okay. And also, so this is the workshop on serverless computing, the on-site version of the workshop, okay, which is done yearly, as I said, in a conference, currently in the middleware conference. But we have also the WoSC10 conference, which is done, or WoSC10 workshop, sorry, which is done periodically online. You can check whether it fits you to show something or do a talk. Usually every new or every scheduled workshop is presented in the Twitter and Blue Sky account of the WoSC, which you have here in the slide. And also, just to know, I guess you know it, but the workshop will be recorded and will be uploaded to YouTube. Okay, so you will be able to find it on the official YouTube page of the workshop, like in the next days. So if you want to see yourselves or a presentation that you liked a lot the next days, you will be able to. Okay. So here we have the committee, which I will not like list it or whatever, but as you can see, we have many people contributing on this, many people participating on this, just to keep on with the quality of the workshop. Okay. And also, just you to know, we will be hosting, like with the same team, the workshop on container technologies of tomorrow. They are not. Only one, the first one. Ay, Dios mío, vale. I feel that's because of the presentation mode. I will just share it, the whole screen, and that should do it.
Yeah, go ahead. Thank you.
Yes. What now?
It's perfect now.
Can you now? Hello? Is it okay?
Everything.
Yes. The thing is that if we put it in presentation mode, it may be lost. And I feel like we don't have time now to correct that.
Yeah, you're on slide 5.
And so, yes, we are doing also tomorrow the workshop on container technologies and container clouds, which will be tomorrow morning. And just you to know, there are some papers in this workshop that may be related to the papers of tomorrow. So if you are interested in that, just come and listen. It will be held here too, I feel. So yes, it's just 2 papers, so should not be like a great effort coming in and listening to them. Okay. and they are pretty interesting. And also, as I said, staying in a schedule is very important. For the ones presenting on site, I will be down here to the right when you are 25 minutes, so that you have 5 minutes left. I will show you a sign just to know, like, to cut things short. And then also when you have 1 minute left. And for the people presenting online, you will hear a duck sound when you have 5 minutes left, like something like that. Okay, but it will not be me doing it. It will be a recorded something. Okay, I could do it too. And also the Zoom link will be open the whole day, and also during breaks. I feel also during the lunchtime. So I will be here around, if not here, like in the coffee room. And if you need help to practice or to set up your presentation or whatever, just talk to me, and we will try not to have problems. Like I am sure that I am committed into it. And last thing, if you have questions, because maybe the time runs out and you cannot ask everything, or you are online and you don't want to ask, or you are ashamed to ask in person or something, please ask your questions in the Discord channel if you can, because the Zoom channel is ephemeral, just as call functions, and the questions might disappear. So if you can, I feel, does everyone have the link to the Discord channel? Yes. So please ask your questions there, and so that we can like keep them persistently. Okay. That's it. You can, if you don't have the link, there you have it. The slides are also in the webpage of the Serverless conference. So if you need it, just go in there. And that's it. That's it. Those are things for later on. So I hope you have a good workshop, that you get some interesting insights on serverless computing. For the ones who are working on it, for the ones who are not, may discover a new trend to do research on. And that would be it. Thank you for coming. Thank you for hearing all these presentators, and we will begin with a workshop. Okay, thank you. So the first one should be.
Hi, Lee, can you start sharing your screen?
Who is presenting remotely? Okay. So Alec, could you make sure he has access and everything? Okay, that's it.
Hello, everyone. Thank you for joining my presentation today. And is it good for me to start?
Yes, I can hear you very well. Herman,
Awesome.
Everything on your side good?
Yes, thank you. Yeah. First, I'd like to express my sincere gratitude to the committee members, organizers, and the technical experts of the workshop and the Midware 2024 for this event possible, and especially express my thanks to Alec. He always give me quick response and continuous support. I am Lee, a PhD candidate from Northeastern University. Today, I will be presenting our paper titled Advancing Serverless Computing for Scalable AI Model Inference, Challenges and Opportunities. The structure of my presentation today includes the following contents. First, the motivation behind conducting this research, the methodology for selecting and analyzing existing works related to AI model inference in the serverless paradigm, and also highlighting the challenges and opportunities in this domain. And we also provide insights and guidelines tailored for both academia and industry. As we know, AI is everywhere. AI is revolutionizing various industries, from agriculture, education, to healthcare and finance, by enabling smart decision-making and enhancing operational efficiency. And the integration of AI into daily life, for example, construction, and ChatGPT highlights the need for scalable AI model inference to support its growing ubiquity. Let's take the large language models as an example. Both the size and the complexity continue to grow rapidly, and one of the largest LMs model, Palm, it has 540 billion parameters. As we know, LLMs involve several key processes, including training, fine-tuning, and inference. But this raises the critical question: where and how should we deploy these massive models? The answer is clear. The cloud provider is almost the best choice. And in recent years, cloud computing as a service evolved significantly, transferring from infrastructure as a service to function as a service. Function as a service is known as serverless computing, and this shift relieves users from the responsibility of managing cloud infrastructure, transferring that burden to cloud providers. Serverless computing is particularly recognized for its ability to scale elastically and its cost-efficient pay-as-you-go billing model. And it makes it an attractive solution for modern applications. And let's consider the most popular open source serverless platform, WoSC, which was first developed by IBM. When users send a bunch of requests to the system, WoSC is able to automatically scale the number of Docker containers to handle these requests. This flexibility frees users from being constrained by a fixed number of resources, enabling them to achieve a balance between performance and cost efficiency. Now, how can AI model inference benefit from the serverless paradigm? Let's explore it further. In this work, we first conducted a comprehensive search for existing works on AI model inference, including machine learning model inference, deep learning inference, and LMs inference using serverless computing. And our sources, including conferences, journals, archive preprints, master's and PhD thesis, and recent innovations from public cloud providers. Through this process, we identified 31 selected works. And the key metrics including the publication date, venues, keywords, and so on. And from this figure, we can observe that AI model inference has emerged as a trending topic. Between 2019 to 2024, it shows an increasing trend. And by the end of August 2024, there were 10 works related to AI model inference deployment with serverless paradigm. And from the 31 selected works, we identified and analyzed the top 10 key research areas. And among these metrics, we can find both resource management and cost effectiveness are the two leading topics. And from the statistics of the 31 selected works, we can find that there are lots of unexplored areas. For example, the model partitioning mechanism, the work is not available at that time. And almost similarly, for batching, there is only one for each in the domain of deep learning inference and LM inference with serverless paradigm. Okay, next, I will introduce how to deploy AI model inference system and how the pipeline looks like. And there are several main components. First, there is user interface, and there is also a load balancer to dispatch the requests. There are storage devices to save the intermediate data and inference results. And there are also virtual machines or Docker containers for the isolated computation. And there is also result delivery. Let's imagine when we ask ChatGPT a question, we would expect the response to be delivered as quickly as possible, the answer to be highly accurate, the cost to remain minimized. And this leads to critical questions. How can these objectives be achieved? And what are the main challenges involved? And what are the opportunities for innovation in this domain? The primary challenges in deploying scalable AI model inference in serverless environments include dynamic workloads, cold start latency, resource inefficiency, and stateful workflows. These challenges highlight the need for innovative solutions to enhance performance and scalability in serverless AI deployment. As illustrated in the figures, during workload peaks, whenever there is burstiness, the corresponding CPU usage exceeds 50% compared to an average utilization of 34% across all available CPUs. And this spike in usage can lead to resource contention and further performance degradation. And a cold start occurs when a Docker container is not yet prepared to load the runtime environment or code logic. As illustrated in this figure, after the keep alive window and before a container is pre-warmed, a cold start is triggered when a function is invoked for execution. This delay can significantly impact performance, especially in latency-sensitive applications. And in terms of resource utilization, both under-provisioning and over-provisioning can lead to performance degradation or highly billing cost. Balancing resource allocation is therefore critical to optimizing performance and cost efficiency. State workflows present a significant challenge in distributed AI model inference system. And this figure illustrates a computer vision task. And there are several processes, including pre-processing, inference, as well as like the prediction output delivery. In a stateful workflow, calculations and the statuses are logically stored together to ensure unified management of messages, access statuses, updates, and function executions during deployment. However, serverless paradigms are inherently stateless due to their short running and lightweight nature. So, what are the optimal strategies to effectively address these challenges while maintaining the benefits of serverless paradigm? Batching, scheduling, resource sharing, and model partitioning are key strategies employed to optimize resource utilization, enhance performance cost efficiency, and address the challenges mentioned earlier. These techniques play a critical role in overcoming the limitations of serverless AI model inference systems. For example, Barista, All-You-Can Inference, and Inflash are frameworks designed to provide optimal resource configurations, and the Mark, batch, and joint batching utilize various batching techniques to minimize cold start latency and maximize GPU efficiency. MOPA, GLIS, and machine learning model composition partition AI models into slices or distribute them across serverless functions. This approach optimizes resource usage, minimizes cold start latency, and ensures compliance with service level objectives. And efficient GPU management techniques such as fast G-share, SMSS, optimized GPU utilization by implementing multiplexing, GPU sharing, and stateful machine learning inference workflows, effectively reduce cold start latency and ensuring service level objectives requirements. Additionally, frameworks like Tetris, GPU cold starts, Viper, and Optimus enhance resource utilization and scalability by employing tensor sharing, remote memory pooling, proactive container scaling, and innovative model transformation mechanisms tailored for high throughput serverless AI deployment systems. Researchers have developed advanced research management frameworks as well. For example, Inference and AmpsInf to optimize serverless AI inference workflows by addressing challenges such as latency, cost, and privacy across heterogeneous execution environments. And the various approaches aim to balance cost and performance for large-scale machine learning inference tasks. FSD inference leverages cloud-based services for efficient inter-process communication, enabling scalable and cost-effective distributed inference, while SFunk separates and fuses tasks for optimized resource allocation and predictive scaling. In addition, MLFast generalizes machine learning inference pipelines by recommending optimal function compositions to enhance quality of service and reduce response time. In this work, we also identified emerging researching areas in the domain of scalable AI model inference using the serverless computing paradigm. This includes serverless LMs inference, AI-driven resource scaling, and enhancing security and privacy in edge computing environments. Serverless LMs inference faces challenges such as high latency from large language model checkpoints and complex GPU loading, but offered untapped potential for cost-effective, performance-optimized solutions like batching and distributed inference. Innovations such as AWS Bedrock, Microsoft Azure AI Studio, LoRa Exchange, Serverless LLM, and Innova address these challenges by enhancing performance, scalability, and latency reduction through novel checkpoint formats, resource-efficient frameworks, and advanced GPU sharing techniques. Serverless platforms typically rely on reactive scaling, but predictive AI-driven models can enhance performance by preemptively allocating resources based on forecasting demand, despite the challenges of accurate predictions in dynamic environments. Solutions like Serving DI, Viper, and Gilis address resource allocation and cold start latency using hybrid scheduling, long short-term memory-based batching, and neural network-driven optimization for inference cost and latency. As serverless computing integrates with machine learning workflows, security and data privacy concerns, particularly in edge computing, have become critical. Frameworks like trusted LM inference use blockchain to ensure trust and verifiability in AI inference, while LM Edge enables local processing of sensitive data, minimizing transmission risks and enhancing real-time privacy-preserving inference. And we also provide valuable insights and practical guidelines for advancing scalable AI inference with serverless computing. Existing serverless AI inference frameworks face limitations such as cold start latency, resource constraints, lack of fine-grained control over hardware, and vendor lock-in with high costs. However, opportunities exist in mitigating cold start issues, implementing predictive scaling, and scheduling for dynamic workloads, and optimizing distributed multi-GPU management. The works on serverless AI inference infrastructures face challenges such as limited capability for large-scale inference due to their stateless nature and delays in real-time applications caused by continuous GPU access requirements. However, opportunities include integrating specialized GPU hardware and AI inference chips while enabling fine-grained control over cloud-based hardware resources. The existing serverless AI inference systems face challenges including high energy consumption for complex AI models, inefficient GPU utilization due to lack of fine-grained control, and redundant energy waste caused by horizontal scaling. But opportunities include implementing advanced cooling systems for inference data centers, developing energy-aware scheduling mechanisms, and employing AI model quantization and pruning to optimize energy efficiency. And the current serverless AI inference pipelines are limited by their modular, stateless, and event-driven nature, which can hinder complex workflows. Opportunities include developing efficient scaling mechanisms, advanced model partitioning strategies, and AI-based optimizations to enhance pipeline performance. The limitations of AI-based optimization include resource unpredictability and the challenges in adapting to real-time inference. However, opportunities lie in offloading AI inference tasks to edge devices for local data processing, enabling privacy-sensitive tasks through federated learning. In conclusion, this study identifies 31 top-tier works among existing literature, marking the first comprehensive survey on serverless and LLM inference. It also analyzes challenges, optimal strategies, and offers valuable insights for both academia and industry. That's the presentation, and I'm happy to take any questions. Thank you.
So, does anyone? Hello. Okay. Does anyone have questions for Lynn? Okay. So, can you hear me?
Yes.
Okay. I have one question that you may not know, but do you know how like commercial products on AI inference, such as AWS Bedrock or like that, how do they work under the hood? Do they use cloud functions, or is there something on that? Or I feel like obviously that's not discovered, but may someone have done some research on that?
Yeah, I did spend some time on the research on AWS Bedrock, and I know they have a lot of pre-trained large language models, and now they use AWS Lambda to manage the serverless pipeline. For example, if you want to summarize a dialogue, audio file, and you can input the audio file and use AWS Lambda to manage the workflow, and you can use an agent to call the large language models, which is saved in AWS Bedrock. I believe they have APIs for users to access. And then they use like S3 as the storage device. And after the inference finished, the results is saved to another S3 bucket, and the user can access AWS to download the results.
Okay. So you can kind of connect lambdas and everything. I'm not very used to that kind of services, but just I was curious on that. Okay, thank you very much.
No
Thank
problem.
you. So
And
So if no one has more questions for Lee,
Mhm.
if someone, thank you, Lee, for your presentation. Was very interesting. Got great insights on that. Also for people who are not especially into AI, they are into serverless but not into AI. Was a great presentation. So
Thank you.
congratulations, Lee.
Thank you.
Thank you. So we may go to the next presentation. If you have, if you have further questions that may come to mind later, just use the Discord channel, okay? And so next presentation will be presented by myself. Here we have. And so share and this. Not this. Here, sorry. Okay. Can you see it? Yeah, well, you can see it.
Yes.
Alex, can you
Good.
see it? Perfect. And
Yes.
can you hear me okay?
it looks good, and I can hear you great.
Perfect. Thank you very much. So, well, I may present myself once again. I'm a PhD student from Universidad Rovira i Virgili from Tarragona. My name is Eizaguirre. And my current work is on serverless resource provisioning in general. However, I am presenting this work, which was done by an previously intern and currently engineer from our group, Usama, who is doing great work on serverless frameworks. I am not especially, I have no special expertise on it. I kind of follow it, but if you have like further questions or maybe deeper questions, it may be better to share them in the Discord channel. I will do my best, but Usama may be able to answer them better. However, I'm delighted to present it today. So this work is focused on also resource provisioning for serverless data analytics, but more in a predictive, in a kind of offline approach. So to begin with, I would like to present LeetOps, who many of you may know, many of you may not. It's not famous or something like very popular, but yes, it has kind of some references and some literature on it. LeetOps is a framework for serverless computing developed originally by our group and IBM, Haifa. And basically, LeetOps provides a framework that tries to bridge the gap between the cloud and the general user, which is kind of the main goal of the serverless, but with very basic primitives, a multi-cloud environment, which you can use. A framework is a framework that you can use either in Azure or in AWS or in Google Cloud if you want. And also, it has integrated MapReduce programming models. It has also kind of tools such as multiprocessing in Python. And it also works with features. So it integrates this kind of primitives and APIs that almost every programmer knows, so that it can be accessible for everyone. And the main thing with LeetOps is that it's really easy to set up and really easy to begin with. LeetOps only needs a configuration file with some cloud credentials and a Python environment, and you can begin deploying your code in the cloud. I feel not for doing much propaganda on it, but it's a very good framework for those people. If you have students that may begin with the cloud, for example, it's a very good entrance to the cloud because it's very easy to use, it's documented, and especially for the first steps in the cloud, it's very useful. Okay, so we have this framework that's, as I said, it's really easy to use and everything. Also, we have tested it and validated it in different pipelines and benchmarks. There is a whole GitHub repository with different pipelines from more like kind of standardized benchmarks such as Monte Carlo simulations or Cummins, but also specific benchmarks, so as water consumption analysis or geospatial analysis. We have also some research works based on LeetOps, and many master thesis students, PhD degree thesis also. We have even production-ready deployments that use LeetOps. For example, the Metaspace project by the European Molecular Biology Laboratory, which does, this is kind of interesting, nothing to do with the presentation, but does mass spectrometry, imaging mass spectrometry results analysis on LeetOps, which basically detects metabolites on biological tissues and gives very interesting results. And we have also in progress projects from external collaborators, which are not strictly associated with LeetOps, such as Cube, which are part of the Pangeo stack, which are geospatial developers, also related to the Dask and Coil project. And they are currently doing in-memory array, bounded in-memory array data analysis on LeetOps and on serverless functions. So we have this kind of standard API, this kind of a very easy to use framework to do serverless computing. And also we have evaluated it on real pipelines and real use cases, which is thing to do, obviously, when you want to provide a product. But we feel that there is something missing in all this LeetOps thing or ecosystem, which is a smart resource provisioning, because that's a thing that many times is not considered in serverless research proposals. That is, you have serverless, in which you abstract the domain of the resource provisioning in the cloud and everything, and you kind of give these layers of abstraction. But then imagine the main goal of the serverless is that democratizing the cloud is it. So what if you want general programmers to program in the cloud, or even we all know this biochemistry, we may not all know, but this is very typical, like a biotechnologist or a biochemistry researcher that has kind of notions in R or in other language and wants to do a parallel computation, but he only knows that like the theoretical principles and that, and does not know how to program it. So if that programmer, general programmer, wanted to run something in the cloud, wouldn't know how many functions to use, what configuration to use exactly, he probably won't. And that's the thing Usama has been working on in this paper. It's providing a layer over LeetOps, which is a programming framework, to intelligently or smartly choosing the number of functions and the memory of the functions and everything that a whole pipeline may need. Because at the end, what we are looking for is kind of a social or kind of a, Nextflow. Nextflow is a pipelining common technology framework for executing bioinformatics tasks. And it has kind of an interface in which people can upload their pipelines, share their pipelines, and kind of contribute between them. If you have, for example, a pipeline on DNA sequencing pipeline or DNA alignment pipeline, you can program it and share it with other users and everything. So we want to create this kind of ecosystem in which people share pipelines without knowing exactly, or without having to know exactly what resources do they need. So Usama has been working on that, automating the resource provisioning of pipelines, which is complex because if you have a multi-stage pipeline, for example, in which, for example, bioinformatics pipelines usually have a kind of tens of stages and everything. And so it's difficult to optimize. And there is a whole research on that he has been doing. And currently, in this method we are presenting here, he has been trying to reduce the amount of samples you need to have to profile a pipeline so that you can get close to optimal configuration. Basically, what he proposes here is a profiling method and an optimizing method that, as you run execution of the pipeline, gets optimized itself, and you reach a point without having to optimize it explicitly, in which the framework itself adjusts the configuration so that you can get close to optimal performance. So you reduce execution time and you also reduce operational costs because you don't have to optimize it yourself and invest time on that. We have some state of the art on that. We have data plug that optimizes the number of functions for data ingestion in serverless pipelines, basically with some heuristics on partition size. We have sizeless and we have many papers on that, on automatic resource provisioning, but not in the number of functions, but in the size of functions, basically reactively, or not reactively, but measuring the like kind of the CPU usage or the memory usage of functions and scaling them up or down to the needs of the execution. And then we have many state-of-the-art proposals, such as Jolteon, Ditto, and Orion are the last ones, but that really optimize the number of functions and optimize the memory needs of functions in data analytics or in pipelines in general. But they are very innovative. They provide very interesting ideas and very contributive ideas, but they are kind of research prototypes that have not been tested in general purpose frameworks, for example. So this work goes more in the direction of testing a real method for optimization in a general framework, and that kind of optimizes a whole list of parameters of the pipeline, not only memory size or CPU requirements of functions, but also packing and everything. Usama used this water consumption pipeline for the optimization, which has 4 stages with different communication patterns between them. Basically, it's a classical data analytics pipeline in which you have a pre-processing stage, then a visualization stage at the end, and some kind of processing at the middle. This water consumption pipeline comes from a European project in which we were collaborating with well, I don't remember right now, but with a business to optimize to port stateful and classical cluster-based pipelines into the serverless for a more elastic and flexible execution. So he tested this method on this. So basically, he did this optimization process, which is what? Sorry. Yes, I can try. Okay, because oh, sorry, yeah, because it's here. How can I? Is it better now? Not very well, but better. Yeah, could be better. It's overflowing. Yeah. Okay. And any ideas on how to solve that? Okay, so if I put this, yeah, sorry. Yeah, sorry, because this comes from here. Yeah. Where? Okay, I may keep it like this. Well, we could remove that. So this is a classical pipeline on data analysis. Okay, and so basically what he did, or what we did, was kind of trying getting a bunch of executions, then extracting the important parameters on those executions, and then using a busted gradient algorithm, distributed algorithm, which is Eizaguirre, which most of you may know, and to optimize it. Okay. It was evaluated on the original parameters that were derived in these others through hyperparameter tuning. And basically what we had is a reduction of 25% of performance. Here we are measuring execution time. Obviously, we could optimize it also in cost, for example, or in performance or in cost performance metrics. Here we are focusing on just performance. And so we get a 25% improvement in execution time across or against the baseline, which was using basically an average of the if you have like kind of different number of functions on each stage, using just the average as kind of a simple heuristic to configure or set up the pipeline. and also a 67% reduction in the, not the execution time, sorry, in the mean average error for a linear regression method. Okay, and also we got a 30% reduction in cost, which, just to make an idea of how we could use it, if we had a framework that executed this pipeline like periodically, and we executed it like 10 times per day for 2 months, we could like already get better or avoid this the cost of profiling. So just the consequence is not as much as the result, but the idea of having an like background process that profiles the pipeline and does some configuration on users execution as they are done. Okay. And so we validated the model and we used different methods. As I said, a busted gradient method, a baseline, the baseline is not optimized, a linear regression, and also a typical PCA for principal component analysis. And basically the boosted gradient method had the better square error. So that's it. It was the best one, and that's it. And so there we are. Key takeaways. So basically, as I said, it's not as much as the result is not like the best insight here. It's better the proposal of having this kind of optimization of pipelines so that end users don't have to optimize their pipelines explicitly, and general users can launch their pipelines in the cloud. Currently, we are working on different methods for this profiling. We are also working on resource provisioning for serverless pipelines in different ways. We are also working in just-in-time optimization of serverless pipelines so that you don't really have to do this profiling of, I don't know, 150 executions. Yes, 150 executions to optimize it so that you can minimize the number of executions or even not do executions to optimize the number of functions, which would be ideal. And we've been working on that for a while, and we feel that's one of the next steps on serverless. Just having the user not to program nothing or to set up literally nothing. So that would be it. The model is generalizable for different clouds, not only because of the model, but also because the framework underneath is multi-cloud, and it makes it pretty practical for any serverless deployment. And that would be it. And next steps, obviously, improving accuracy, which is a general next step for an AI optimization. Also, exploring advanced architectures, where with what we mean with that is just not testing kind of data analytics pipelines, which may be the typical stage after stage execution, but a more complex flows of serverless functions, which may be more difficult to optimize, and also validating on diverse pipelines. I feel also one next step could be optimizing both in cost and in execution time, because imagine you can have the best execution time with 1,000 functions, but it costs you like 10 times more dollars. It should be not the case. Okay. So, well, kind of bureaucracy things. It was funded by the Ministry of Economic Affairs and the CloudSkin European projects. This work was done in collaboration of Alterna Technologies, which is agriculture business in Murcia, Spain. And thank you for listening. Thank you for being here. And if you have any questions, feel free to ask. Thank you. And a special thanks to Usama for this work. And if you don't have any questions, we can go to the coffee break. Energy savings. What are energy savings? That's a good question. Do you hear me? Yes, that's a good question. I feel that's kind of a trend that has been ignored in the serverless for until now. There has been some research on it recently, and I can tell you that we have a paper on it this workshop also. I feel Etienne is talking about energy savings in serverless environments. The thing with energy savings here is, from the point of view we are talking about in this paper, in this work, which is like so many layers up to the cloud provider or the function provider, because we have function provider or the serverless provider, then we have a framework, then we have the end user. It's difficult to optimize on energy savings because the end user has really no connection with it. But from a cloud provider perspective, I'm pretty sure it's an interesting matter, because even currently, like there is a trend also. AWS Lambda is porting and giving more options on executing ARM CPUs for their execution. So they are for sure concerned about that. It's sometimes difficult to kind of have a big picture on energy consumption, because we don't have the scale and the cluster size of a real cloud provider, but we can do some work on that. I feel that is a trend, that is something to tackle, obviously, but we have to separate it from the kind of end user optimization, end user experience of the serverless, and the serverless provider experience, in the sense that the end user should not be aware of the energy usage, because it's rare to have its serverless execution done in a proprietary cluster. But yes, from the provider side, yeah, that would be it. Yes. What, sorry? Well, not that shouldn't, but it's difficult for it to be aware, is it? They should be concerned, obviously. Well, yes, but kind of they should be concerned. Of course they should, but it's like this idea of, for example, when you have a Google Drive or a Google Photos in which you upload a photo, and you, instead of uploading a single photo, you upload 15 photos because you do kind of many replicas of each photo. You have to be aware, yes, but will users then, they can be aware, but will they really do a energy aware scheduling of their functions if they are not the providers of the underlying infrastructure? I don't know. Do you feel so? Yeah, could be. So could be. How could you, for example, if you are working on a abstracted framework, how could you like kind of transfer, or kind of how do you call it, give user reasons to save energy? Incentives, that's it. I didn't. Yeah. In fact, I said that should not be like a concern of the user, but seems a pretty good idea, because if you had an interface that showed you the efficiency of your pipelines, that's pretty attractive. Yeah. I feel, yeah. At first I didn't see it, but I feel that's like kind of a thing to optimize on. Yes. Yeah. I like it. Yeah. So definitely, I don't have like a specific answer right now, but I will definitely think on it. Yeah. Thank you. Yeah.
Yeah, thanks for your talk, and thanks for all the work. I have a question regarding the data sets that you showed, or that you talked about. I think what we're missing as community are some standardized workloads like the CB community has. for example, with the standardized data sets. Are these projects that you mentioned, could that be something that could be standard workloads for us?
Yes, could be. Well, it's difficult to say in a way because, for example, this water consumption pipeline that we used in this work obviously is related to a specific business model, and it's difficult to standardize these kind of things. However, there are other patterns that has been repeated somehow in the serverless community. For example, the Monte Carlo simulation is a pretty kind of repetitive pattern in serverless benchmarking. Also, like papers adore executing terasorts in serverless functions, which is kind of pretty an anti-pattern, but it's kind of the worst case scenario for serverless functions because as you need indirect communication, it shows the deficiencies of most architectures. And we also have a terasort benchmark on the GitHub page also. So yeah, they could be things to consider because also, what do you need as a serverless benchmark? There are two kinds of benchmarks. You have, on the one side, this typical like trace-based benchmark in which Azure or someone publishes its traces, and you have your serverless architecture that runs them, and you check how the scheduling is done and what is the performance. And then we have these kind of benchmarks that are kind of data analytics or kind of pipeline benchmarks, which are more unexplored. And yeah, they could potentially, of course, be more standardized benchmarks. But there should be someone that told us because we have like communities, but we don't have a serverless consortium or something that could like generalize it. And we need like kind of an authority to say that. But yeah, of course, that is a good idea, yes. So thank you for listening once again. I feel we are just in time to go to the coffee break. Afterwards, I feel, Alec, am I correct? We are beginning at 1:45. Yes. No, we are having lunch then.
Oh, there is a lunch break, I think you
We
have.
have lunch. Yes. Okay. Perfect.
Just come back like 5 minutes before, so there is one remote speaker, right?
Okay.
So they
Sure.
can, check their.
I will be. However, we can come 5 minutes before. I will be here 15 minutes before, just if someone has doubts or something, or if you need help. Okay. Yes.
Sounds good.
Yeah.
See
Okay.
you then.
So, Alec, do you have something to say?
No, I was saying, see you then. After, hopefully, you get good lunch.
Yes. See you.